Record. Okay. Okay, so this is where we left off in our notes yesterday. And so before we move on, let's make sure we remember what we're looking at. Okay, so when we're looking at this structure here of our notes, what is this structure representing? This whole physical structure. The thylakoid membrane. Excellent. So all of these like dependent reactions and the chlorophyll are all found in the thylakoid membrane. Okay, so in reviewing the process, remember we started out with, this is our reactants for the photosynthesis reactions, and we're focusing with light and water in the light-dependent reactions. Light comes into our photosystem 2, energizes an electron, which goes through the electron transport chain. Okay, and in doing so, it will operate proton pumps to pump these hydrogen ions into the inner thylakoid space, which is also called a lumen. And then the electron that's energized is then replaced because the Z complex of this photosystem is going to oxidize this water and essentially split it into, it's releasing the electron, a hydrogen ion, and then oxygen gas. So that's where we left yesterday. Oh, and then we use the storage of the concentration of hydrogen ions, and then we use that to, with the ATP synthase and this protein channel, to diffuse the hydrogen ions back through the thylakoid membrane with their concentration gradient and generating ATP. So that's what we did yesterday. We have one more part, really. Actually two, but more like one. So basically, we started out with photosystem 2, and you're probably wondering, where's photosystem 1? Well, it comes in our order. It's coming after photosystem 2. Not because it really comes in order, but this is the order of discovery. So photosystem 2 is further along, also in the thylakoid membrane. Or that's just two, I meant one. Photosystem 1. It's hard to remember, it's backwards. And photosystem 1 is very much like photosystem 2 in that it also has a reaction center. Or a reaction center, which is where I'm going to find the chlorophyll A. And it also has pigments, chlorophyll and other pigments. Yes?
Does photosystem 1 have to go between the electron transport chain and ATP synthase? Or can it go anywhere in the membrane?
It actually does go in between, and the reason it goes in between is because of what's happening with the electrons. Because there's actually, what happens is the electron that is released from this electron transport chain actually enters another smaller electron transport chain that I'm not drawing because it doesn't have a protein channel, so we're just going to kind of ignore it, but it's actually there. But we're just going to skip it and show that the electron eventually makes its way to the reaction center of photosystem 1. This is the electron that's released. And the reason it goes there is, one, the reaction center has an electron acceptor, and it needs the electron because when the light comes in, just like when the light comes into the other photosystem, gets funneled through, and it causes an electron from that photosystem to be energized. So it's a replacing electron that's energized. So that's why, that's how it fits in between. Okay. All right, so this is what's happening to the electron in photosystem. You notice that this is not actually generating ATP this time. It's not operating a protein channel. But it is, this electron energy is going to be captured, though, by an electron acceptor molecule called NADP, or NADP+. NADP+. So we're just going to draw, and you don't really have to know a whole lot about it other than it's called NADP+. captures an electron, and then it will combine that electron with some hydrogen ions that are hanging around in the stroma, and it will create or combine to form NADPH, which is another energy storing molecule, energy carrying molecule, kind of like ATP is. Very unstable, so it has a lot of energy to release. So we have actually made two energy storing molecules with the light dependent reaction of photosynthesis here. Okay, so we've made two. So we've got the NADPH, and I'm going to go ahead and put my little energizing swivels around the ATP, because ATP is my other energy storing. So this actually is phase one for the light-dependent reactions of photosynthesis. And the next phase that we're going to learn about next week, well, phase two, sometimes called the dark reactions, or the light-independent reactions. And they don't need light. They don't have to have it in the dark. They just don't need light, because they get their energy from somewhere else. Where do you think they get its energy? Yeah.
The light-dependent reaction.
Right, it gets from the molecules that we created, that we showed here. So what happens is this NADPH and the ATP are both going on to the dark or light independent reactions. I'm going to put a star because I didn't leave myself enough room, and I'm going to write it over here. So we'll say ATP and NADPH. They are used in light independent. Reactions. This is my reaction.
Would you like some white out?
I've given up on the one. Okay. I actually have correcting tape, which I'm not using. Okay. All right, so that is what we've done. So let's go ahead and take a look at the Word version of this to make sure that it makes sense with what we've got with our full drawing now. So now we've got a sketch, and we've also got the Word version.
This is why you use erasable pens.
So we've got, okay, first of all, I crossed something out here because I decided I didn't like it, and we're going to change it. So the first thing it said, in the overview, we talked about all this machinery, or all the parts of this were in the walls of the thiocyte. Well, those aren't really walls, that's the membrane. So let's call it what it is and cross out wall and write membrane. That's the first thing we're going to do. All right, so then we showed how the pigments are all energized by the light, and that water is split, releasing oxygen, and then the hydrogen ions are trapped inside the thylakoid for use in light-independent reactions, and we generate ATP, so that's shown. Okay, we already talked about the Z complex yesterday, and then we also talked about photosystem 2 yesterday, and then we talked about chemiosmosis, except we did not talk about F, which we can now talk about. And that is that the electron, which has released its energy, is then passed on to photosystem 1. So that was the new part today, the electron going from photosystem 2 to photosystem 1. So we have that. And then in photosystem 1, we see that it is also energized, and it charges an electron that loses, basically it loses the high energy electron, because the electron is going to go to the NADP and become NADPH, so that the energy can then be transferred to next, the light independent reactions. And this part C is something that we just want to notice about. We're going to be learning some different reactions that have multiple steps. And this particular reaction, it's first of all, it's non-cyclic, because the electron that's transferred, I can follow its progress in a linear fashion, and I can see where the electron comes from, and I can see where the electron leaves, and it doesn't cycle through again. So that means it's non-cyclic. And it's photophosphorylation because we phosphorylated the ADP, the ATP, and we got our energy from light, from photons. So that's why it's called photophosphorylation. It is non-cyclic. Okay, so that's another thing to know. We're going to learn some other things that are cyclic in nature, so learn to recognize those just in general as we go throughout all the processes, like not just now, but even the future units. Just you'll start to recognize things that are cyclic and things that are not. Okay. Does anybody have questions on these steps or any of the things we talked about yesterday or today about these?
Are they in order?
What?
Are they in order?
Are they in order? This is pretty much in order, yes. One of the questions has to do with which one of these happens first, whether it's the Z complex or the light. I think you could put either one of those to be first in the way we're doing that because they kind of happen at the same time. You know, you energize, lose an electron, and then replace it. Well, at the same time. And this is actually, we're showing the sequence of events, but they are also occurring at the same time, although there's a sequence as far as the flow of the electrons. So that's the order we're talking about, the electron flow. Okay. All right. Questions on any of that? All right.